Good afternoon. This is a talk about the application of the idea of adaptive synergies to a humanoid hand. This is a joint work with Manuel Catalano, Giorgio Grioli, Alessandro Serio, Edoardo Farnioli, Cristina Piazza, and myself. Let me start with the clips from a pretty old videotape we took in 1989. At that time, very nice robot hands were already available. This is the JPL Stanford or Ken Salisbury's hand. And these videos show that the hand, equipped with intrinsic tactile sensors, were already able to measure friction coefficients and do some other very dexterous manipulations as detecting objects by texture, reflex control of grasping, reacting to external forces by increasing the grasp force, and follow and reconstruct shape. So these kind of hands have been around for some time now. What is the motivation for doing further research on hands? Well, if we look back at those pictures, you can see the motor box on the robot arm or the Bowden cables. The hand itself is nice and looks in dimensions and size similar to that of a human hand, but the actuation was still very complex. Now the real point in progressing in hand research is how to make hands simpler. And of course the target is that of human hands. In other terms, the talk is about simpler hands and how the design of those simpler hands is not necessarily easier. Indeed, human hands are a complex system that is made of many bones, arteries, veins. The ligaments and muscles system is astounding, and the numbers themselves, we have 29 major joints in the hand, we have 34 muscles moving the fingers and the thumb, 48 naming nerves, 30 or more named arteries in the hand. So the question is, how can the brain cope with such a complexity and drive the system to the nimble operation and powerful operations that we know? There has been some quite a few thinking about this problem in the neurosciences. And there is neuroscientific evidence that there exist sensory motor synergies and constraints. This goes back to the earliest time of neuroscience, but quantitative work on hand postural synergies date back only 15 years or so. There is an important paper by Marco Santello, Flanders, and Schötting that collected and analyzed statistics of a large database of human grasps. So what are synergies? Synergies are the principal components of grasp covariance matrix in the language used in that paper. And the explanation of this principal component is that they compose the hand movements in some primitives that are shown in these short clips. If we compose the first two synergies, the first two columns of this matrix, we obtain already 84% of the variance, and the first three account for 90% of the covariance. Already the first synergy is able to lead the hand of a very simple brain, that of a baby, in doing effective grasps. How, if we model a hand with only a limited number of synergies, can we obtain a dexterous or powerful hand? There is a straightforward kinematic interpretation to synergies that basically model the hand velocities as belonging to the tangent bundle and the tangent vectors being the columns of this synergy matrix S. Then the fingers will move according to the hand Jacobian. Let me illustrate how the hand would move under this geometric interpretation of synergies. The hand shown here is moving according to the first synergy, the first principal component of the synergy matrix, and it's closing from sigma 1 equal to 0 to sigma 1 equal to 1, progressing in the closure. When the hand, though, closes on an object, then we have a problem with this rigid model of synergies. Indeed, as far as the first contact occurs between the hand and the object itself, the hand has no possibility of going further in closing the grasp, because either the finger will stop there or will get inside the object. Therefore, the shape of the hand does not necessarily comply to any specific object that you want to grasp. How do we really get a grasp then? Key point is how forces are applied and controlled, and this geometric synergy model that has been used in the past cannot really account for grasping force generation. What relation then is there between grasping forces, grasping posture, and synergies? So, how can we have rigid models of synergies and grasps? Well, the answer is that human hands are not rigid, and this should be considered. Human hands indeed have compliance of the musculoskeletal system, of the skin, and the objects themselves sometimes are compliant. So these combine in an overall grasp stiffness matrix K. And if we consider this and we put this model in the grasping equations, then we can come up with a model of synergies that we have called soft synergies, according to which the geometric synergies that we have seen in hand posture principal component analysis only drive a inner hand representation. The hand represented, the virtual hand would go inside the object, but the real compliant hand is only attracted by this inner model and repelled by contact forces on the object, thus reaching an equilibrium and applying forces on the object. This model of soft synergies has been proposed and verified in studies before. Now, time is come for applying this in Hands for Robots. Hands for Robots have been around for quite some time, but as we said before, many of those are too complicated for real-world application, for robust and powerful hands, or for prosthesis. So let's consider how hands can be actuated. First, very direct method is to apply full actuation. That means one joint, one model. Of course, this concept is very straightforward. You have an independent control of the degrees of freedom. The contrary to this approach is that it's an encumbrant, it costs, it has weight, and complex programming. A first hand that we developed in the Hand Embodied project is a hand that replicates the kinematics of the human hands and has full actuation, meaning every joint as a model. Then how can you use synergies? Well, you can use synergies for doing correlation of joint movements, and in a software implementation, you can solve some complication of the control, meaning that you can use fewer degrees of freedom to actuate the 16 degrees of freedom of this hand, and have, as a consequence, a programming of the hand which is more easy. Still, the mechanical complexity remains very high, and that hand indeed is not applicable in situations such as prosthetics, where you need less weight and less cost. Another possible application is to use synergies mechanically in a direct way. Idea is to implement the first case synergies with pulley trains. Every pulley train here on the right drives a model of the hand. Here is the pulley train, and here is the connection to the tendons. By rotating this shaft, pulleys will pull down these tendons, which will actuate the contacts on the fingers. There is another synergy will be on this train here, and you can combine the synergies according to the synergy model that we had described before. There are advantages that the control space is a natural synergy space, and we use less motors than before. On the other hand, the implementation, and here is a very interesting implementation by Brown and Azada in 2007 of this concept, has a disadvantage that the application of grasp has no adaptivity. There are few contact points, and the grasp force control is insufficient, as discussed before, for rigid models of synergies. As I mentioned quickly, the introduction of the idea of soft synergies allows to generate forces in a more natural way. Here is a video where the inner model of the hand, driven by the synergy geometry, is shown by the meshed hand. The wireframe hand is the inner model, and the real hand is depicted here with the rendered hand. In this case, the generation and control of force is simple, and grasps are effective and stable. On the other hand, the implementation of this model poses some problems. You could realize this model by simply introducing springs or compliant elements between the mechanical synergy that we saw before and the joints. However, this did not lead us to an efficient mechanical design for quite some time. So we were confronted with this difficulty of implementing a nice theoretical idea that could solve the problem and could not find a nice mechanical solution. So we went looking around and we studied in detail a seemingly unrelated approach, that of under-actuation. In under-actuation, basically actuate more joints with fewer motors. And a classical application of under-actuation is differential gears. And any car you have a differential mechanism for driving the two wheels in the rear train, if you have a forward drive, with one single motor. There is a congruence equation, which is a geometric equation, that tells you that the positions of the two wheels are not completely defined by the position of the motor, rather their sum is. The mechanism, as a consequence, has self-motions that are generated by this mechanism. The mechanism is such as to distribute the forces of the motor on the wheels. Can we apply this general idea to hands? Of course, yes. You can generalize this to actuating more joints with few motors using cascaded differential mechanisms. And here is a conceptual scheme of how you can do this. So the actuator would move this force F, and this pulley would pull on this cable here, and then actuate the three joints, distributing the actuation force in the three joints here. Of course, this mechanism has self-motions, which is useful to adapt shape to that of objects. Of course, you can use passive elements to balance pressurized forces, for instance, springs, clutches, stops. What are the advantages? Of course, you can realize this in small size, little weight, low cost. It's an adaptable, enveloping grasp that is generated. The idea is not quite new. Indeed, one of the very earliest hands that we have had in robotics and prosthetics is the University of Southern California Belgrade hand, dating back to 1962, was realized using adaptive under-actuation. What are the cons? Well, so far, the theoretical underpinnings of the design procedure for such hands were not clearly spelled out. However, many hands have been designed, for instance, the Hirose and Numetani hand in 1978, or more recently, the hand from Laval University in 2002, which is shown here, and several others more recently. Question is, we have a nice idea about how things should be done according to this model of soft synergies, and we have a nice method that works well, which is under-actuation. Can we mix the two? Can they have any point of meeting? Well, so let's study the model for these adaptive under-actuated systems. And if we look at the model of how the contact forces are balanced, we need to introduce two matrices. One is matrix R, which is the matrix for the radii of the pulleys, and one is matrix E, which is the matrix for the elastic coefficient of the springs or elastic elements that are in the system. We have an equation here, and if we rewrite this equation in matrix form, we can solve this equation and achieve a description of the positions that the hand will achieve according to a matrix times the contact forces on the fingers and summed with a matrix times the reference that you put in the system. So the two matrices here are called A and B, and you can observe that the matrix B, which is this part here, multiplies a reference vector which can be interpreted exactly as the soft synergy reference that we have seen before. So if you now are able to build such a matrix as you have in this equation to be equal to the principal components that you are interested in replicating, then you can achieve the behavior of the synergies that you wanted to achieve with the original design. A straightforward solution for this equation exists and is shown in this case, and this is what we had in our design. So the problem whether we should use soft synergies or under-actuation can be solved by this, and indeed we can use under-actuation to achieve the model of soft synergies by applying this equation and solution. So we come up with a design that in principle allowed us to use the technology of under-actuation to implement soft synergies. First implementation that we gave for this idea is through a hand that we consider a sort of a mechanism of synergies, whereby you can combine differential mechanisms in a system where every stage can actuate a different synergy and compose them, summing them into this model of adaptive synergies and moving this hand. The hand has been built and some experimental results have been achieved. For instance, here you can see how the hand complies actively, adaptively to different objects. The hand moves and you can sum different synergies. For instance, you see composition of first and second synergy, first and third synergies on the right. It seems to be a good idea, but of course the mechanical implementation is not so convincing in this hand. So we went forward and we tackled the next step of the design process. So we went back to the drawing board, we optimized the design, and then we introduced some innovation. A first of which is looking at the articular joints and soft ligaments. We wanted to introduce something that was similar. And here you can see how the new design replaces revolving bearings and mechanical gears with a completely new design where you have rolling contacts and soft ligaments. You can see that the new finger can be used, that can be banged on a table without getting damaged. You can even displace its components. So this led us finally to the PISA IIT SoftHand design that I will show here. Here is a hand that is multi-degrees of freedom, anthropomorphic, and is actuated by this adaptive synergies model. You can see the hand grasping different objects and adapting its shape to that of the object so as to grasp in a stable and robust way. The hand can grab a pen, a cup, a glass, and can be driven to write letters. Of course, this is a hand that has 18 anthropomorphic degrees of freedom, but only uses one soft synergy. That means one single motor. It's a drastic simplification with respect to the earlier designs. The new version of the hand is now red and is completely self-contained. All motors and batteries are contained in the hand, and only this connection is bringing the signals for opening or closing the hand. In this video you can see Christina wearing a human interface that allows her to actuate the hand and show how the hand can be used in grasping different objects. Here are some more objects that Christina is successfully manipulating. The hand is mounted here on a robot arm and grabs different objects. Again, the hand is only actuated by one motor. There is no sophisticated software to control the hand. It's simply an open, closed control. All the intelligence of the hand is embodied in its mechanical design and low-level control design. Here is the hand grasping max, and again, the position of the hand with respect to the hand is different. Therefore, the hand behaves in a different way and shapes itself as to have the best grasp for the Mac. Different phones can be grasped again, or any different objects of very different shapes. Here a handle is managed. The hand can also grasp bottles, as in these videos here. And what is interesting is that we're also able to grab them quickly, as we do in quickly passing and grabbing an object on the fly. The hand is designed for robustness and safety. The soft design of the ligaments and the joints is able to withstand many manipulations that you see here from the real hand of Manuel Catalano, one of the authors. And here is the hand moving against obstacles and showing that it can withstand robustly these impacts. We refer here to Marcus Grebenstein of DLR, who introduced the idea of a robustness test for robots, which we find very interesting and worth trying. The hand is soft, but yet it's strong. And as you can see here, can open a sugar jar, can withstand disturbances, and can apply quite strong forces. We can do elementary force control in this phase. The hand is now controlled with only 1 degree of freedom. Still, we can increase the force and, for instance, decide when to spray using this bottle. So with this, I conclude the presentation of the soft hand from PISA IIT, and I would like to thank my co-authors and all the group that have participated, together with the sponsors and the Centro E.Piaggio and IIT who cooperated in this project. Thank you very much.